In the spring of 2024, researchers at Tianjin University published a thermal efficiency figure for an ammonia-fueled engine that stopped the engineering community cold, 44.7%. Let me tell you what that means in plain English. The best gasoline engine Toyota ever built tops out at 41% under ideal conditions. This engine beat it by nearly 4 points on a fuel every major automotive research body had formally classified as non-viable for combustion. You heard that right. A fuel the industry rejected is now outperforming the best gasoline technology on Earth. And that is just the beginning, because the efficiency number is not the real story. The fuel itself is. Hit a quick like and subscribe so you do not miss the next one. By the end of this video, you are going to understand exactly why this result changes the energy calculus for every sector that runs on combustion. For decades, the internal combustion engine industry operated under a ceiling that felt less like an engineering limitation and more like a law of nature. Thermal efficiency, the percentage of fuel energy that actually becomes motion, had been climbing since the first gasoline engines turned over in the 1880s. But by the early 2000s, that climb had slowed to a crawl. By 2015, the sharpest engineering teams in the world had converged on roughly the same conclusion. Somewhere between 40 and 42% was the practical ceiling, and getting past it would require either a fundamental rethinking of combustion chemistry or a fuel nobody had seriously considered. Here's the detail that puts everything into perspective. When you burn gasoline in an engine, roughly 60 to 70% of the energy in that fuel never reaches your wheels. It bleeds out through the exhaust pipe as heat. It radiates through the engine block into the surrounding air. It disappears into friction between moving parts running at temperatures high enough to melt aluminum without active cooling. The engine in a standard passenger car is, at its core, a very expensive heat generator that occasionally moves a vehicle as a secondary function. Most people who drive every day have never thought about this. The wall has a formal name in engineering circles, and it comes from the second law of thermodynamics. No heat engine can convert all of its input energy into work, because some of that energy must flow from hot to cold to make the cycle run at all. Picture a furnace the size of a shoebox, running at over 3,000 degrees Fahrenheit at its peak, trying to push a piston while losing heat through every surface it touches. That is your engine. The gap between peak combustion temperature and exhaust temperature determines how much work you can extract. Widen it, and efficiency climbs. Every material science and combustion chemistry limit in the book constrains how wide that gap can realistically get. Toyota got closer than anyone. Their dynamic force engine, introduced in 2018, achieved 41% brake thermal efficiency, a figure that required variable compression ratios, laser-ignited combustion, and a decade of computational fluid dynamics work. Mazda's Skyactiv X followed a different path using compression ignition of gasoline. Independent assessments from the Society of Automotive Engineers confirmed that further gains from gasoline chemistry alone would require combustion pressures that current engine materials could not survive. Most people who follow this space know the 41% figure. What most of them never hear is what came next. As extraordinary as that summit was, the more interesting question was never whether gasoline could go further. It was whether anyone had been staring at the wrong fuel for 30 years. The announcement came in 2021. A research team at Tianjin University published preliminary results for an internal combustion engine running on ammonia. Not as a fuel additive, not as a hydrogen carrier burned in a fuel cell, but as the primary combustion fuel in a modified reciprocating engine. The engineering establishment's response was swift, largely dismissive, and almost entirely focused on a single objection. Ammonia burns too slowly. They were not wrong about the chemistry. Ammonia's flame speed in open air measures approximately 0.07 meters per second. Gasoline's flame speed is roughly 0.37 meters per second, more than 5 times faster. In a high-speed internal combustion engine, where each combustion event lasts a few milliseconds and the piston is already moving away from top dead center before the flame front fully develops, that gap is not a minor inconvenience. It is, by standard engineering logic, a fundamental disqualifier. The Society of Automotive Engineers had formally assessed ammonia as a combustion fuel candidate in the early 2000s and concluded that its low flame speed made high-efficiency combustion impossible without radical engine redesign that would destroy any cost advantage the fuel might offer. Ammonia had other problems on the resume. Its energy density by weight runs approximately 9,000 BTU per pound, compared to gasoline at roughly 20,000 BTU per pound. It is corrosive to copper alloys and certain seals commonly used in fuel systems. Its narrow flammability range, between 15 and 28% concentration in air, leaves almost no margin for mixture error. On paper, it read like a list of reasons written specifically to disqualify a fuel from serious consideration. They said the same thing about diesel. Rudolf Diesel proposed slow compression ignition combustion in 1893 and was told by the engineering consensus of the day that slow combustion was an inherently inefficient process that could never compete with the fast-burning fuels of the era. We all know how that ended. The Tianjin team was not naive about the objections. Their program, which expanded significantly between 2021 and 2023 with backing from China's Ministry of Science and Technology, was built on a specific hypothesis: that the flame speed problem was not a property of ammonia that had to be accepted, but a combustion parameter that could be engineered around. What they proposed to do about it was the part the mainstream coverage missed almost entirely. Here is where the consensus broke. The solution was not a new engine. It was a new relationship between ammonia and a second molecule it already contained. Ammonia is not a mystery compound. Every chemistry student knows it as NH3, one nitrogen atom bonded to 3 hydrogen atoms. And hydrogen, unlike ammonia, burns extremely fast. Its flame speed in air runs approximately 3 meters per second, more than 40 times faster than ammonia alone. The question the Tianjin team asked was deceptively simple. What if you did not have to choose between them? Picture a campfire built from damp wood. The wood will burn eventually, but it catches slowly, smolders inconsistently, and produces a flame front that never quite reaches the temperature the fire needs to sustain itself cleanly. Now picture adding a handful of dry kindling directly to the center of that pile before you light it. The kindling ignites fast, builds heat rapidly, and pulls the damp wood into a sustained, stable combustion event that the wood could never have achieved alone. You have not replaced the damp wood. You have amplified it with a fraction of a faster fuel. That is the operating principle of ammonia-hydrogen co-combustion. And the Tianjin architecture takes it one step further, because the hydrogen does not come from a separate tank. Inside the engine system, a small portion of the ammonia fuel flow is diverted before it reaches the combustion chamber. It passes over a ruthenium-based cracking catalyst, operating at approximately 1,400 degrees Fahrenheit. At that temperature, the catalyst breaks the NH3 molecules apart, releasing hydrogen gas and nitrogen. That hydrogen, typically between 5 and 20% of the total fuel volume depending on engine load, is then mixed back with the remaining uncracked ammonia and injected into the combustion chamber together. The result is a blended fuel stream that burns with a flame speed and stability profile that conventional ammonia combustion cannot approach. The part most coverage of this technology never reaches is this. The cracking reaction happens continuously inside the engine system itself, driven by waste heat recovered from the exhaust. The hydrogen production requires no external energy input, no separate pressurized storage, no dedicated refueling infrastructure. The engine makes its own combustion accelerant from the same fuel it is already burning. Tianjin's published trial data showed cycle-to-cycle combustion variation, the standard measure of combustion instability, dropping to levels comparable to a well-tuned gasoline engine. That is not a marginal improvement. That is a complete reclassification of ammonia's combustion behavior. The flame speed problem was solved, but solving it exposed something the team had not fully anticipated. And here's what nobody mentions when they celebrate the co-combustion breakthrough. Ammonia contains nitrogen. Nitrogen at high combustion temperatures reacts with oxygen to form nitrogen oxides, NOx, a class of compounds that sit at the center of emissions regulations in every major economy on Earth, the US EPA tier. 3 standard caps. NOx output from passenger vehicles at 0.03 grams per mile. Uncontrolled ammonia combustion can produce NOx concentrations that blow past that threshold by a significant margin, and ammonia has a second emissions problem that gasoline does not. Ammonia slip, unburned ammonia passing through the exhaust system, which is toxic at concentrations above 25 parts per million and carries its own regulatory ceiling under Clean Air Act standards. The standard engineering response to toxic combustion byproducts is to cool the burn and enrich the fuel mixture. A richer, cooler combustion event produces less NOx because peak temperatures stay lower, and lower temperatures mean less thermal nitrogen fixation. It sounds logical. It is also precisely the wrong move for an ammonia-hydrogen engine trying to achieve record thermal efficiency. Richer combustion at lower temperatures destroys the efficiency gain the co-combustion architecture just delivered. You solve the emissions problem and lose the efficiency record in the same breath. This is where the solution sounds like it should not work, and that is exactly why it does. The Tianjin team ran the combustion leaner and hotter, the opposite of the conventional fix. A lean burn at elevated temperatures maximizes the temperature differential across the combustion cycle, which is exactly what drives thermal efficiency upward. But lean, hot combustion in an ammonia-hydrogen engine produces a NOx load that standard exhaust handling cannot manage. So they paired the lean burn combustion strategy with a selective catalytic reduction after-treatment system, an SCR unit that injects a precisely metered urea solution into the exhaust stream, triggering a catalytic reaction that converts nitrogen oxides into nitrogen gas and water vapor. Both are chemically inert. Neither carries a regulatory burden. The combined result, NOx, output in the Tianjin test cycle measured below 0.02 grams per mile equivalent, inside EPA Tier 3 limits, achieved while running the combustion event in the configuration that produces peak efficiency. Ammonia slip measured below 5 parts per million at the tailpipe. The SCR system handled the NOx load the lean burn produced. The lean burn delivered the efficiency the program was chasing. Neither system compromised the other. Running hotter and leaner produced cleaner output. The conventional logic was wrong. 3 subsystems, each one solving a different problem, each one generating conditions that the other 2 must continuously compensate for in real time. The cracking catalyst adjusts hydrogen output based on engine load. The combustion chamber receives a fuel blend that changes composition from one operating point to the next. The SCR system must meter urea dosing against a NOx load that fluctuates with every shift in combustion temperature. Run any one of them on a fixed map, static fuel tables, predetermined injection timing, set and forget catalyst temperatures, and the efficiency figure collapses. The system only performs at its certified level when all 3 subsystems respond to each other dynamically, cycle by cycle, at engine speeds where each combustion event lasts roughly 4 to 8 milliseconds. Picture a conductor standing in front of 3 instrument sections that are each playing a different tempo. The strings are running on ammonia's slow combustion rhythm. The brass are firing on hydrogen's fast burn. The percussion is the after-treatment system, responding to what the other 2 sections just produced. The conductor's job is not to pick one tempo and impose it on all 3. It is to read what each section is doing in real time and adjust the others to match. Remove the conductor and you get noise. Add a conductor fast enough to respond in milliseconds and you get a system that performs above what any single section could achieve alone. The Tianjin team's solution was a closed-loop combustion management architecture, a real-time control system that monitors in-cylinder pressure, exhaust gas composition, catalyst bed temperature, and cracking conversion rate simultaneously, then adjusts injection timing, hydrogen fraction, and urea dosing on a cycle-by-cycle basis. At an operating speed of 3,000 revolutions per minute, the system processes and responds to new combustion data roughly 50 times per second. The number that rarely makes it into public reporting is the response latency requirement. The control system must complete its feedback loop in under 2 milliseconds, tit per cycle, or the efficiency optimization falls apart entirely. When the 3 subsystems operate under closed-loop coordination, the architecture achieves what the individual mechanisms could not independently produce. Tianjin's published results in the journal Fuel, verified by independent measurement at the Chinese National Engineering Research Center for Internal Combustion Engines, recorded a brake thermal efficiency of 44.7%, achieved at a continuous operating load representative of real-world driving cycles, not a single-point laboratory optimum. That is not a laboratory anomaly. That is a repeatable, independently verified result on a configuration with a direct path to production. But the internal verification was only the first confirmation. What the independent body found when they ran the same test was not what anyone expected. Here is the honest picture. Ammonia today is produced almost entirely through the Haber-Bosch process, which runs on natural gas. Approximately 90% of the 180 million tons of ammonia synthesized globally each year is classified as gray ammonia, made with fossil fuel energy, carrying a carbon footprint that partially offsets the combustion efficiency gains this engine delivers. Green ammonia, produced by splitting water with renewable electricity, exists in demonstration quantities. It does not yet exist at the commercial scale the shipping and trucking industries would require. Anyone who presents this engine result as a fully solved, ready-to-deploy emission solution is skipping the supply chain problem that sits between the test cell and the fuel pump. That problem is real. It is also a manufacturing and infrastructure challenge, not a chemistry one. And manufacturing and infrastructure challenges have a historical track record of responding to economic pressure in ways that pure chemistry problems do not. With that acknowledged, the Chinese National Engineering Research Center for Internal Combustion Engines independently measured the Tianjin engine's brake thermal efficiency at 44.7% under sustained load conditions in 2024. For context, the diesel engines powering the global long-haul trucking fleet average approximately 43% thermal efficiency under ideal highway conditions. And that figure took 70 years of refinement to reach. A long-haul truck running 100,000 miles per year on diesel burns approximately 15,000 gallons of fuel. At equivalent energy output, an ammonia-fueled powertrain operating at 44.7% efficiency would require a fuel volume that costs at current industrial ammonia pricing roughly 30% less per unit of work produced. Over a fleet of 100,000 trucks, a mid-sized logistics operation, that gap is measured in hundreds of millions of dollars annually. The combustion byproduct profile is equally significant. The primary exhaust products of the ammonia-hydrogen engine under SCR aftertreatment are nitrogen and water vapor. The carbon dioxide output is zero at the point of combustion. A diesel equivalent producing the same work output emits approximately 160 grams of CO2 per mile. The tailpipe of this engine, running on green ammonia, emits none. That is not a marginal improvement on diesel. That is a structural replacement of diesel's emissions profile using an engine architecture that fits inside the same space as the powertrain it replaces. If that number changed how you see this technology, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover what comes next. The efficiency result is proven. The emissions math is verified. The question nobody had fully answered was which industries were about to feel it first. Roughly 13% of global carbon dioxide emissions come from sectors that battery electrification cannot currently serve at commercial scale. That figure comes from the International Energy Agency's 2023 World Energy Outlook, and it refers specifically to deep-sea shipping, heavy long-haul trucking, and grid-scale backup power generation. Industries where energy density requirements exceed what lithium-ion battery technology can deliver at economically viable weight and volume. The gap is not a minor engineering footnote. The best lithium-ion battery cells available today store approximately 250 to 300 watt-hours per kilogram. Diesel fuel stores approximately 12,000 watt-hours per kilogram, roughly 40 times more energy per pound than the best commercial battery chemistry. A trans-Pacific container ship running on batteries would need to dedicate the majority of its cargo hold to the pack required to complete the voyage. The ship would still not make it. This is not a cost problem, it is a physics problem, and it is exactly the reason the International Maritime Organization's 2023 decarbonization strategy explicitly identifies ammonia as one of two primary zero-carbon fuel candidates for deep-sea vessels. Here is the number that most analysts miss entirely. Approximately 400 million tons of ammonia already moves through existing global production, storage, and distribution networks every year. The global port infrastructure handles liquid ammonia at commercial scale right now. No new refueling network is required. The pipes, tanks, and loading terminals exist. Ammonia stores as a liquid at minus 28 degrees Fahrenheit at atmospheric pressure, cold but manageable with standard industrial refrigeration. Hydrogen, by comparison, requires either compression to 10,000 pounds per square inch or liquefaction at minus 423 degrees Fahrenheit. That storage and handling gap eliminates the infrastructure barrier that blocked hydrogen combustion engines for 3 decades, not by solving it, by bypassing it with a molecule that already has a global logistics network built around it. MAN Energy Solutions and Wärtsilä have both announced ammonia-compatible marine engine programs targeting commercial deployment before 2030. The historical parallel is instructive. When diesel began displacing coal in marine shipping in the 1920s, industry analysts estimated the transition would take 50 years. It took 15. The onboard cracking architecture delivers the same category of advantage diesel delivered then. A genuine technical edge that cannot be replicated by simply copying a patent, because the advantage is embedded in how the system works, not in what it is made of. The engineering limit was technical, not political, not economic, technical, and it has been resolved. What comes next is not a question of whether this changes the industry, it is a question of how fast. The combustion engine was supposed to be a casualty of the energy transition. Every credible roadmap published between 2015 and 2020 assumed it would be phased out, replaced by battery electric systems and hydrogen fuel cells on a timeline measured in decades. What the Tianjin result forces onto the table is a possibility those roadmaps did not model, that the combustion engine, given the right fuel, might not be the technology being replaced. It might be the transition vehicle itself. The architecture that carries the sectors which cannot electrify across the gap to the zero-carbon future those roadmaps are chasing. That is not a minor revision to the conventional story. That is a different story entirely. If you made it this far, you now understand more about ammonia combustion than most people who write about it for a living. What was actually proven in that Tianjin test cell is this: a closed-loop ammonia-hydrogen engine using onboard catalytic cracking and selective catalytic reduction after treatment achieved 44.7% brake thermal efficiency with near zero tailpipe carbon output, surpassing the best gasoline engine ever produced on a fuel with an existing global supply chain in a configuration with a direct path to production. The mechanisms are not exotic. The materials are not rare. The infrastructure already exists. What was missing was proof that 3 simultaneous subsystems could be coordinated precisely enough to beat a ceiling the entire industry had agreed was fixed. That proof now exists. The sectors that cannot wait for batteries have taken notice. The question that remains, the one that will determine how fast this technology moves, is not whether ammonia combustion is viable. That question was answered in a test cell in 2024. The question now is whether the green ammonia supply chain can scale fast enough to match an engine technology that has already arrived ahead of schedule. That gap between the proven engineering and the unfinished infrastructure is where the next decade of energy transition plays out. And it is a gap that economic pressure, not additional chemistry, will eventually close. If this changed how you think about the future of combustion, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think ammonia-fueled engines are the real bridge fuel the energy transition needs? Or is this just buying time for battery and fuel cell technology that will eventually close the energy density gap anyway? Both sides of that argument have serious engineering behind them, and I want to know where you land.